Today is what, lecture 4, right? Okay, guys, we have lec- lecture 4. What is the date today? 22nd, 01/22. Okay. So we were doing these. Did I get a book? Yeah.
Yes.
So we are doing chapter 3 where we were discussing, existence and uniqueness of solutions. And if you remember it, it was all connected to Lipschitz conditions, right?
Right.
So, and if you remember the lemma 3.1 that we did last time, right? Like lemma. So Lipschitz, global, local, did you understand that, right? It all basically depends on that constant, Lipschitz constant, which is positive, what is the domain in which it can define a single constant and say that Lipschitz property is satisfied in that domain, okay? And we will take some examples, don't worry about it so far. So lemma 3.1 basically was showing that, del f by del x so if we can show this, right, if we can say that del f by del x is less than equal to L, if we can find a bound that the Jacobian or the slope of the function is bounded by L, then basically you can also say, I'm just rephrasing the lemma, that is also your Lipschitz constant. Tz Lipschitz constant. So that's one way to compute your Lipschitz constant. If you are able to show that within a domain that slope or the partial fraction or Jacobian with respect to x of that function is bounded by L, that L also can be used as Lipschitz constant, right? So that was lemma 3.1. Okay. And so going forward, we have lemma 3.2. basically it says if f of tx and del f of del x, so both this and this, we are talking about that the function as well as this Jacobian are continuous for some domain D, which is a subset of Rn, then f is locally Lipschitz. You see what we are getting to is locally Lipschitz in X on AB into that domain. So AB is the time interval. So in this domain, we are Lipschitz. So if this exists, right, that naturally guarantees that at least it is locally Lipschitz. If so, for example, if you want to take an example, let's go a little forward. So for example, f of x equals to x squared, right? So this is continuous for sure, right? And then what is f del f by del x is 2x, that are continuous 2x, right? Then this guarantees that it is at least locally Lipschitz. Why? See if I say that.
So I have to prove that it's continuous to be, like the derivative has to be locally Lipschitz. That's it.
Derivative has to be continuous and this has to be continuous. Means it has to, right?
Okay, because
see, continuous means no discontinuities. So x square is continuous, x is continuous, 2 of x. So see, function 2 of x as well x square, both are continuous.
So, but the only thing, both f and df dx have to be continuous, and those are the only requirements to say that
it is locally Lipschitz. Exactly. And why?
Okay.
And let me show you why. Because let's say, and it's in a domain. It's not that.
With it, right? Because both of those approach infinity as time.
Yeah, exactly. So if I say, let's say
so
x, x is bounded by this 2, right?
Okay.
That means plus minus 2. Then I can say that I can put a bound on this. right? You can find an L. So that guarantees that it is locally. So as long as del f by del x is continuous, it is definitely locally Lipschitz.
Okay.
So that kind of guarantees that it is locally Lipschitz. So that's one test, right? That's a very good test. See,
Like those are what's confusing. Like I'll read it and it just doesn't.
For example, like if you have some discontinuities or something, that thing is not differentiable at that point. So that means that won't be locally Lipschitz.
So it's defined within that boundary, means it has a value, right? So
Yep.
the 3.1 is also satisfied, isn't it?
Yep. 3.1 is satisfied. Yes, exactly. So basically 3.2 came because of 3.1, because we can use 3.1 to prove this condition that when it is continuous, when del f by del x is continuous, this is more important. So basically that means this is a bigger condition,
Right.
overarching condition. So if this is there, then it is locally Lipschitz. If it is locally Lipschitz, does not mean that you will be continuous. Del f by del x will be. The reverse is not case. So what we are saying is continuous implies this, the reverse, that it is locally Lipschitz. It is locally Lipschitz does not imply that it will be continuous. So don't, okay? That's very important.
So if df dx is continuous, that also always means f of x is continuous, right?
Yeah.
Okay. But if f of x is continuous, df dx is not necessarily continuous.
Yeah. For example,
because I think that's kind of in here, but all
for example, f of x is, let's say, 2x. So the derivative is just 2, right?
Yes, 2. Okay.
Or some saturation function or something where the function is continuous, but that is not continuous. No,
They're both are.
but yeah, like there can be some discontinuity, like because when you differentiate something and
Like
it is
1 over x,
divide by
that's
0
a
error
little
or something.
Yeah. Okay.
that come.
So what this sounds like is saying, as long as df dx or del f del x is continuous, you know it's locally Lipschitz.
Exactly.
That's all it is.
That's all it
That's
is.
that simple.
That's
okay.
simple. Yep. Right. So.
But that's what this is saying mathematically. So if f of x and dfd are continuous on, what's this AB?
AB is the time interval.
By d, what does that mean?
Means your time comes from between A and B, and your x comes from D.
Okay, for some domain. Now what does this symbol
The
versus
in.
this symbol mean?
That is in.
This
and
is
in. No, the bottom one is in.
Okay.
That is in
Like
this
in
set.
that domain,
in
right?
that set.
Okay, in that
And
set.
and then that one is subset.
Oh,
So R, the D is a subset of R.
okay. All right.
So R is a bigger whole field, right?
Okay.
And I'm saying D is this. So this let's say this white space is Rn, right?
Let me just write that home. D
Is-
is subset of R. D is sub. Because all that was
Yeah,
confusing.
subset of R.
Okay.
Okay.
All right. So if f and now continuous on, we said that is time domain and that's for the x domain. For some domain, we'll do
And the proof
subset
is very
of R.
simple. You can use
So
3.1.
so on that.
And the proof is very simple. You can use 3.1. As soon as you show that they are continuous, and you fix a boundary or domain, then you will see that
You know, it makes sense.
You,
Yeah, it
you
makes
can get
sense.
a L.
Okay, but yeah.
As soon as you get L, 3.1 says that you got a Lipschitz constant, right?
Right.
So that's the objective here. So next lemma is 3.1. Oh, sorry, not 3.3.
Right.
3.3. Lemma.
All right, this is starting to make sense. You're answering my questions already. All right, cool.
Lemma 3.3 is saying that if, so now we are going further, that what can we say about global Lipschitzness? Right now it's local.
Right.
What kind of conditions we want to impose mathematically to make it local? So if f of tx and if del f by del x are continuous, so we know that guarantees local Lipschitzness, right? This
Right.
statements. If f of tx and are continuous, then they are locally Lipschitz. And then f is globally Lipschitz in x if and only if. So we are adding an additional condition.
Right.
If and only if del f by del x is uniformly bounded. Uniformly bounded. Okay, so if you can say that, say in the previous condition, what we were saying, all we were saying
It's
they
just
should be continuous.
Yeah.
Now we are saying if you can say that del f by del x is uniformly bounded. Now we are not in that, then it is globally Lipschitz. Okay, so let's. I can give you an example, right? Bounded in Rn, right? Now we are saying it should be like, for example, f of x equals to 2x. Is that example? It's a linear, but it is continuous. This is, I think this is also continuous. F prime x of equal to 2 is also continuous because it's a constant line.
It is, yeah.
It is continuous, but now it is uniformly bounded. That means it is this function is globally Lipschitz. And you can see that there is a solution that exists because it's a linear system and all that stuff. Okay, so let's take an example here. So it's additional condition. Del f by del x exists, is continuous, and if it is bounded in Rn, then it is globally Lipschitz. Okay, you can say that the same L works for the whole space.
Right.
Yeah, so we are just increasing the domain from D to Rn.
Exactly. No, but now the additional is that bounded.
Yeah. Initially it was bounded in that small domain.
So it was not bounded as such. It was just continuous. Bounded because it was continuous. You could bound it because in the domain.
Yeah.
So for example will be this: f of x equals to minus x1 plus x1 plus x2, x2 minus x1 minus x2. What can we say about this? F of x is continuous for sure, right?
Yeah.
We can say that f of x is continuous. Okay, is it continuously differentiable? We can find out.
Yeah.
Like if we do del f by del x, it should be simply minus 1 plus x2 x1 minus x2 1 minus x1, right? That is del f by del x. That is also continuous,
Yeah.
right? So that means at least we know that this is locally Lipschitz.
Right.
That is, at least it is locally Lipschitz. And then you can go further to see if it is, locally Lipschitz, del f by del x bounded or continuous does not mean, it means it is locally Lipschitz, but it does not mean that it is not globally Lipschitz. If we go and show that this is bounded also,
That means it's
then it will be locally Lipschitz, right? So let's see if we can show it is bounded. So now to make it bounded, we should use norms, right? So we have to find a norm of this del f by del x. Right, so let's find a norm. So let's find an infinity norm. You know infinity norm? Infinity norm is basically the maximum. I can write it as maximum of the column, the row sums, right? So maximum of minus 1 plus x2 plus x1. So that's 1. So that's this one, right? So if you add absolute value of these two.
Okay, so that's the max of the row.
And then maximum, and then it will be of again it will be of x2 plus 1 minus x1, right? Absolute value of these two. So that's the infinity norm, right? And let's say if you say so this is too small, but if I say that we defined a set W where x belongs to R square. R square means a two-space domain, so where x1 is less than equal to a1 and x2 is less than equal to, the absolute value of x2 is less than equal to a2, right? So that's where we are defining a W. So see, now I'm sure that if you find this thing in the Rn space, definitely is not bounded, right? Because x2 goes to infinity, x1 goes to infinity, everything goes to infinity. So we have to put a set to see if, at least in a set, if that is bounded or not, right? So if we plug in these values, right, so the maximum value comes out to be, for example, minus 1 plus x2 plus x1 will be what? What is the, we have to say, we have to maximize, right? So we have to plug in the maximum values, right? So 1 plus x2 should be like, let's say when you take absolute value of this, it will become 1 plus x2, right? Plus x1. So this is what it is. When you take, so this is minus 1 plus x2 absolute value, right?
Okay.
So this is less than equal to, so do you know this theorem? A plus b is less than equal to a plus b, right? So same thing we are applying here, right? It is 1 plus x2 plus x1. And now you can plug in the values. It is equal, less than equal to 1 plus, what is x2? It is a2 plus a1, right? What is the max? We have to say how, when is this quantity maximized? When x2 is maximum and when x1 is maximum, right? At the boundaries. So this is maximized. Similarly, this is equal to, and same thing will come if you find the maximum value of this quantity, right? So that also comes out to be 1 plus. So same thing, like also this quantity also come out to be 1 plus a1 plus a2. So that means what is the maximum value of this? 1 plus a1 plus a2. So that means your del f by del x can be written as, in at least in this frame, in W, can be written as infinity norm, can be written as 1 plus a1 plus a2. You will have to use norms for finding the bounds, so otherwise, right? So that is your L actually. This is your L. You can use this as a Lipschitz constant. Okay, so this is how you find L. But this is locally Lipschitz. Or at least globally Lipschitz in W.
Less than that, right?
Yeah, in this you can say that there is one L that works for everything.
Right.
Okay. So you can take one more example here. Let's take one more example. Example is, let's say we have f of x equals to x2 minus saturation. Now see, real non-linearities are coming. x1 plus x2. Okay. So that's the saturation function, and this is not, so f of x, it's for sure because of this saturation function is not continuously differentiable in R square at least. Means in whole domain this is not continuously differentiable. The previous function, if you see, at least it was continuously differentiable, that at least we could say that it is locally Lipschitz.
Right.
To find L, we have to put bounds that, to find when, we say let's find it in W. But here it kind of defeats this. So it means, then can you say that it is not locally Lipschitz? No, right? You have to go do more testing. But if it was continuously differentiable, you could say that, hey, yeah, it is locally Lipschitz. But if it is not, then you cannot say that it is not.
Okay. So just because it's not, it could still be. Hey, it could still be.
We thought you left the class.
I'm sorry, I was reading papers and lost track of time.
No problem.
So even if it's not differentiable, it actually still could be. Okay.
Exactly, but that was sufficient condition.
Right.
But it is not necessary condition.
The opposite. Okay. That's what that means. Okay.
It is sufficient. Say it is continuously differentiation. Yes.
Okay.
Go ahead and say that it is locally Lipschitz.
Okay.
But it is not necessary that if it is not continuously differentiable, it is locally Lipschitz or not. So we have to do some more testing then. We have to go more. You have to actually go and find bounds and all that jazz. Okay. So just to do that, so what we do? How do we do? Let us check. So we actually go then to the basics, saying let's actually go ahead and check that Lipschitz function and compute it and see if we can show. Because what was that? That was saying f of x minus f of y less than equal to L x minus y, right? So now actually we will have to go and compute this quantity, because if we can show this, then it is still, we can chase Lipschitz, right? So let's use two norm here, because again the norms depends on what you have in hand, which norm is easier to operate, right? When you have matrices or things like that, it's easier to have maybe infinity norm. But so depends. That's why two examples are there. There we used in previous example infinity norm. Here we will use two norm. You have to select one norm to these are norms, right? This can be a second norm or infinity norm, but both the norms should be same on both sides.
Right.
At least that should be the case, right? Let's choose. So there is one. So this saturation function, right? Saturation itself. Let's say saturation of eta minus saturation of zeta. There are two values, right? The same thing. Like if I have a space, and there's a point called eta. There's another point called zeta, and basically all you're doing is dealing with the because everything else makes sense. Saturation function has a special property that we are. It can be shown that it is eta minus zeta. It is, right? That's true for a saturation function. You can verify. What is a saturation function? Is basically what? A saturation function is like you go here and you saturate, right? So basically you can verify that if both the points are here, like let's say I choose a point here and I choose a point here, it will still be less than x minus y because the function and if these 2 points are there, this is linear curve, so that's not a problem. So this is the property you can verify it's always satisfied. So saturation of x minus saturation of y will be less than equal to x minus y. Right?
Yes. Okay.
Always. Because
It means it saturates with positive value only.
No, it's negative here. But see, these values, right? This means absolute values, right? We are finding norms.
What if the saturated value of that zeta is negative?
Where?
So it will make it positive, isn't it?
This saturation is a function of eta and zeta. For example, saturation function is like, let's say it's plus 2 and minus 2, right? After some value of epsilon, right? Epsilon is like after 1, it saturates. So depending on, what happens to the function, it saturates after 1. You can always make it, the saturation function can always be normalized like a unity and saturates at plus 1 and minus 1. So I didn't understand your question again. Come.
So is the nature of saturation function always like that?
Yeah, it is always. Saturation means after that it will never increase. It stabilizes, right? So it's increasing, and after this point it saturates. So that means the slope becomes 0 at this point.
Yeah, so it's always positive in right.
Yeah. Why would it go negative?
Like if there's a way that it can shift up and down, is there a way?
It means if it is below this, then it will not saturate. Then if it is here, it's so you can have function like if there's a function doing this, but saturation function generally is defined like this, that there is a between these limits it is linear, y equals to x, and right. So we have a function, right? For
so
example,
that slope always has to be 1.
So that slope is always 45 degrees.
And it's always positive. It can't be a negative 1. Okay.
Okay.
That's what you were kind of
Yeah.
asking. He's
Okay.
wondering if the shape could go here, then go negative, and then go.
So the saturation function is generally defined like you have the it's linear, or like it's y equals to x in this boundary
Between x and
between
y.
then, and then it is 1 and minus 1 if it is above that value. You can define what that value can be where it will saturate. So you can define a saturation function in that way. But yes, general saturation function like you have unity slope and then plus minus 1. Okay. So that's true for this. Now let's see what can we do here. Next page, the previous page. Here, so my f of x is this, right? So we have to compute this quantity. Okay. And remember, x is a vector. So x is x1, x2. There are 2 variables, and y, the second point. So we can also have 2 points, right? X and y. So and y is y1 and y2, right? This is a vector. So we have to use the vector notation. So now the objective is to compute this. Okay. And what is the second norm? of a matrix, for example, you have, let's say I have x1 and x2. What is the second norm of this?
Distance, is
It's going to
Is
be,
that what it is? Euclidean distance?
yeah,
Okay.
it's going to be
Square root of
x1
x1
x1 squared plus x2 squared, right? So that's if I am towards second norm of this, second norm squared. Okay. So now what we are doing, we are finding second norm of this quantity. So we will have to do like something like f of x minus f of y is the second norm. What is that? So that is equal to, less than equal to, we will have, so the first quantity is simple, it is x2, right? So the first, so this is this squared plus this squared, right? So x2 minus y2 squared. See, so it has to be x2 minus, so it will be x2 minus y2 squared plus, we can use this condition now here, because the next one is saturation, right? Saturation of this minus saturation of y, saturation of x minus saturation of y, right? Here, so for this, like, it will be x1 plus x2 minus saturation of y1 plus y2, right?
Where are you putting x1 minus x? Okay.
So for this it was, see, when I take a difference of two functions, right, f of x minus, let's write this, right? First let's write what is f of x minus f of y. Less than equal to, that is x2 minus y2 minus of saturation, what is that? x2 plus x1 minus plus saturation of y2 plus y1, right? This is what I'm writing. So what is the second norm of this vector? This vector will be x2 minus y2 whole squared plus, now we know this condition, right? So we have this minus this saturation function, and we can apply this this inequality, that saturation of eta minus saturation of zeta is eta minus zeta. Similarly, we have this quantity, right? y2 of y1 minus saturation of x2 plus x1, what will be that? That will be simply this, right? So it will be x1 plus x minus y is eta, so that will be, so that's minus, we're doing minus, right? So minus of this becomes plus, so so it should be something like this, y2 plus y1 minus x2 minus so minus x2 plus x1, right? And whole squared of this, right? We're just using this condition, eta minus zeta, and then we are doing the squared of this term, right? So that, then we can open it up now, is equal to x1, if you open this thing, right, now this squared, this, so you can write this, now you can see, you can rewrite this, it will be, one will be y2 minus x2 in the squared term, other thing will be y1 minus x1, right? I can rewrite this squared, I'm just rewriting this, and then it will be x2 minus y2 whole squared, and then basically we are just applying math and saying, hey, now just open the square, what is this, is a, this is b, so it is x2 minus y2 whole square plus y2 minus x2. Again, because this is a squared term, right, I can always write x2 minus y2, it doesn't matter, because it's a positive quantity always, right? And then x1 minus y1 whole square and plus twice of
y2 minus x2
of x1 minus y1
minus x1.
and x2 minus y2, right? So I can write this. So this is what your f of x minus f of y second norm is coming out to be, less than equal to this quantity. Okay, this quantity. And now, do you think this looks like something? It's a quadratic expression. Now this will add, right? What is this? X2 minus Y2 will add. So it becomes less than equal to twice of X2 minus Y2 whole squared plus X1 minus Y1 whole squared plus this twice of X1 minus Y1 X2 minus Y2, right? Do you think you can write this as a matrix now? I can,
Probably.
right? So we can write this as a matrix. See, this is a, if you remember, X transpose Q X, right? Something like this. Do you remember this? Like if there is a positive definite matrix and you multiply. So for example, what is the, when I have 1 0 0 1, right? And I have let's say X transpose Q, what was that? X, yeah. So this is, let's say I have X comma Y and I have X comma Y. What is this multiplication comes out to be? If it is just an identity matrix, it comes out to be
X squared, Y squared.
X square plus Y square, right? So an X square can Y square can be written like this, right? X Y multiplied by the matrix multiplied by X Y again. So this is X transpose Q into X. So this is a Q matrix, right? So X square Y square can be written like this. Similarly, this is a squared matrix as well. So you see how we can write this as a matrix. Now you get an idea. We can write it like this. We can say X1 minus Y1 is a vector, X2 minus Y2 is a vector, right? A matrix where X1 Y1 is just single, so that's 1. This one is twice, right? So that's 2. And then this is 2, so you can come 1 and 1 because they're 1 here and 1 here because they add up, right? And that will be equal to X1 Y1 X2 Y2. This basically can be written as a matrix. Okay, a quadratic term. A quadratic equation can always be written as a matrix. So this vector multiplied by this matrix into. So what does this mean? That means so we can write this like this, right? So we have X minus Y transpose. X is a vector into this matrix 1 1 1 2 into X minus Y, right? So now this is our f of X minus f of Y. Again, as I said, why we need math is because when we go into norms and all, you have to come up with this. This is the second norm now. What can do you remember some conditions of positive definite matrices? If you remember, this is a positive definite matrix. Can you, right? It has
Everything's positive.
everything is
Yeah.
positive. Eigenvalues are positive. Not everything is positive, but the
Right,
determinant
right.
is positive, and then the cofactors 1. This is positive, and the determinant is positive. So 2 minus 1 is positive. So it's a positive definite matrix. What can you say about positive definite matrices? Do you remember that condition?
Energy.
So if I have a X transpose QX, right, I can say that this is equal to less than equal to lambda max
I remember
of
that.
Q, lambda max of Q into X squared, and it is less than equal to lambda min of Q into X squared, right? So we can now write this as X squared. So this can be written as so our f of X minus f of Y of second norm now can be written as this matrix, whereas X minus Y transpose Q, X minus Y is less than equal to lambda max of Q into X squared, X minus Y squared, sorry. Okay, so that is, what do you think it looks like? It looks like L to me. So I'm saying f of X minus f of Y second norm is less than equal to a lambda max of that Q matrix into x minus y squared. Doesn't it look like a L to you guys? Like L, right? So that is my L. That's how you find L when if I use a second norm. Like, so what is lambda max Q? In that case, it comes out to be under root of 2.618. So that's my lambda max of this matrix 1 1 1 2. So that means this square root of 2.618 x minus y. Right? It looks like that, right? So this is f of x minus y, and we showed that now the Lipschitz condition holds. Right? So what that means? So this is actually this is like globally Lipschitz. Even though there is a saturation function. And why saturation doesn't matter? Because see, I can always give a slope like this or something, right? Not a slope like this, like you can have some slope which bounds
Right.
these two. That's why I can say that it is a globally Lipschitz function, even though it was not continuously differentiable. It is still globally Lipschitz quantity because of this. Now it's true everywhere, right? This not like I'm saying it's not valid here or there. It's all the time valid. So that one L is valid for this function, saying this is globally Lipschitz. That function. Okay. Now there is a. Now we will see what is the effect on the existence. If you remember our first theorem where we said if your function is locally Lipschitz, there exists a solution, unique solution for time t0 plus delta. You remember that theorem? Now we will that was locally. What happens when we say it is globally Lipschitz? Right? So that's the next thing that is coming up. Questions? I know. This is welcome to grad level classes. Yes, the 7,000 level. So, and we are not using like as any out of the world things. We were talking about norms. This is the first time we are using a norm like to compute something. So, okay. The math is same, but this time you are actually applying math to see what actually happens there. But in linear systems, everything came out to be eigenvalues and all. But here, every problem is different. Some things can be shown. Okay, it's continuous. Good. If it's not continuous, let's investigate again. Their game was over, right? Eigenvalues played and said everything about, but here things are not like that. Great. So let's give this theorem 3.2. No, before that, let's take an example. One more example I want to take. Example. And the example is this. Let's say we have x dot equals to minus x square, right? And let's say x of 0 equals to minus 1. What can you say about the Lipschitz? We are talking about now x of 0 equals to minus 1. So initial condition is given, f of x is given, and we are talking about the solutions. So first thing comes whether, let's check its Lipschitzness, right? It is globally Lipschitz, locally Lipschitz. What is that? What can you say about it? At least it is locally Lipschitz. It is locally Lipschitz because it is continuous and it is continuously differentiable, right? So that sets that at least it is, so it is continuous. F of x is continuous and f del f by del x is also continuous, right? Because it is one is minus x square, one is minus 2x, right? So now at least it is locally, that implies it is locally Lipschitz at least. So and when we solve this equation, you can always solve like if you apply your differential equation solving qualities, the solution comes out to be x of t equals to 1 over t minus 1. Hey, applying this initial condition, right? So this is the, so what, right? A solution exists over, so there is a boundary over which solution exists, 0, 1. So it never touches 1, because it touches 1 when time touches,
It goes infinity.
yeah, right? So as t goes to 1, x goes to infinity, right? So the solution kind of, it leaves the compact set at t equals to 1 actually. So that's finite scape time. That's the example of finite scape time, that in 1 t equals to 1, exactly at t equals to 1 second it will disappear. The solution will disappear, right? So this is example 3.3, right? 3.3, right? So that's the finite. But in the view of discussion of example 3.3, when is it guaranteed that solution can be extended indefinitely, right? So that means there is a solution till t equals to 1. The local Lipschitzness, if you remember that theorem, it says if it is locally Lipschitz, then there is going to be a unique solution for t 0 plus delta. So here that's exactly the same thing, right? At t equals to 1, game over. So for 1 second you can guarantee that there is a unique solution. After that, so what else can we do? Right? So local Lipschitzness at least guarantees that will be a solution for some time interval. And it is locally Lipschitz, right? So that ties up to that. So let's see, next theorem basically kind of fills that gap, because we are interested in unique solutions for longer intervals or infinite amount, like forever. So for that there is theorem 3.2. Okay, it's called global existence and uniqueness. Okay, and it says f of tx is piecewise continuous, at least. For example, your saturation function is a piecewise continuous example, because it is only discontinuous where the
At
slope
those
changes.
dots, yeah.
Slope changes. Otherwise, it's a piecewise continuous example, right? So it's at least it's a piecewise continuous. F of tx at least is piecewise continuous, and it satisfies this our Lipschitz condition, f of tx minus f of t comma y less than equal to L x minus y, right? For all x comma y belongs to Rn. What does that mean? That means it is globally Lipschitz. When that happens, what does that mean? It is globally Lipschitz, right? When you satisfy this condition for all space Rn, that means it is globally Lipschitz. And then for all t belonging to t0, t1, so between a time interval, if it is globally Lipschitz, then x dot equals to f of tx with x of t0 belonging to x0 has a unique solution over t0 comma t1. Okay, so now we are saying if you have a time interval, right, t1, infinitely or big time interval, where you can show that function is globally Lipschitz, there is a unique solution. Okay, and like you can think of we can take an example, but proof is again in appendix. We can go there. Okay, we'll take. But the problem is another. But this is a very big condition.
Right.
Most of the time, things will not be globally Lipschitz. That's like guaranteed. Only functions like x dot equals to ax, which are linear, are globally Lipschitz. And they have a unique solution for sure for time, extended period of time. Right? But now what? What can we do with local Lipschitzness? What additional things we need to do to local? So that's for sure that we want a good unique solution for extended period of time, even if it is locally elliptious. That is the goal now, right? That's what will be more practical. This is not practical. You will go and see, you'll find none of your equations are globally elliptious, actually. So with local elliptiousness, what can we do? So let's say, let's take an example before we go there. It's called example 3.5. 3.5. So we have electronic copy of the book. We'll get you that from someone, and we got one more copy. So whoever is talking more, like Samir and you talk more, so then maybe Scott can have this copy, and then we're trying to get one more copy, but I think we'll send
I don't
electronic.
mind having a digital copy. I might prefer it. You can send me a digital
Okay,
copy.
yeah, we'll ask Anushna to send that. Okay, so let's say x dot equals to minus x cube. Okay, and what can you say about this? We are trying to talk about the Lipschitz global solution. So it is continuously differentiable, right? That's very easy to show. That means it is locally Lipschitz.
Right.
But finding it's not globally Lipschitz for sure, because it's. But do you have because del f by del x equals to minus 3x squared, and you can never bound it, like unless you fix a boundary,
Right.
you can never bound it. That also gives you a very good, interesting point. If I can keep something in that boundary, then things are good, right? Yeah, then it is, at least you can say that is globally Lipschitz for that set.
Right.
Then you can, so this is interesting property here, because this is a stable system. X dot equals to minus x cube. Doesn't matter where this point will start, it will always go to the origin. This is a stable system, like x dot equals to minus x, like it has negative eigenvalues if you think from that perspective. And because of that, this solution will never leave this boundary, right? Whatever boundary you want to draw, wherever you start, that's a boundary. So that means if I have a boundary, then I can always put a bound on it, right? I can find an L. So that means our next theorem will say something like this: it is locally Lipschitz, and as long as x of t never leaves a set domain D, then you can say that you will have a unique solution, because it never leaves that set, and in that set it is always Lipschitz. That it's like saying it is globally Lipschitz. Like, it doesn't matter where you start, you will always come to the origin. So you can always draw a set and saying, once it starts here, I can draw a boundary that it will never leave this set. So if you can provide that kind of condition, that okay, local Lipschitzness is good, but what if we can say that instead of saying it is globally, we can say that it never leaves a set, and within this set it is at least you can find a Lipschitz condition. Okay, so that's the kind of example. Because this has a unique solution, right? X of t, I'm just writing the solution, sine of x0 squared plus 1 plus 2 x0 squared t minus t0. So it has a unique solution, and this is the unique solution, SIGN, sine of x0 squared. So when you solve this, you will get, when you solve an ODE, you will get this solution. So there is a unique solution, even though it was, and this is always like any it's for forever, the solution is there. Doesn't matter what your t is, you keep changing your t, it is not going to infinity or something, it is a solution, right? So that means other than having being at local Lipschitz, the additional condition was that because I know that this is stable and it never leaves that set, that initial condition boundary, that means okay, so that's a good condition. So that means stable systems are helping you there, right? Because that okay, so next theorem says this, theorem 3.3. Theorem 3.3 says if f of tx is again piecewise continuous in t and locally Lipschitz, right? Locally Lipschitz means what? In x for all t greater than t0, right? And all x in D subset of Rn, then let W be a compact subset of D. I will give you these definitions. I think they are in the notes also. Before we start chapter 3, there are these definitions. What is a compact set and all that stuff of D.
Before we start, which chapter?
Chapter 3.
This is chapter.
In the notes.
Oh.
In the notes, not here.
Oh.
So in the notes, if you just there are definitions of like what is a, and suppose it is known, because if a system is stable, then it is known, right? It is known, and later in chapter 4 we will connect all these dots, right? If it is known that let me check my message here, David. Just text this, I guess. And suppose it is known that every solution of x dot equals to f of tx, x of t0 of x0 lies entirely in W, then there is a unique solution that is defined for all t greater than equal to t0. That is a very important theorem, because this will because that's what we will be doing in stability. We will be using Lyapunov functions to show that this solution never leaves this particular set. That will be the whole, like, holy grail for this this subject here, that if you can see that the solution does not leave a compact set, then it's at least a stable system, right? At least a stable system. You got that point, right? So now I gave that example, right? If you can say that, okay, it is locally Lipschitz, and then additionally you can say that there is a subset W, right, in which you can show that solution never leaves that subset, it lies entirely there, then it is Lipschitz. Okay. And how did I know that? For example, this x dot equals to minus x cube. Let's choose a energy function half x squared, right? That's my energy, right? So what is my initial energy? V0 will be half of x0 squared, right? That's my half initial energy. What is V dot? So this is always positive. Energy is always positive except at the origin. Except at the origin, this is always positive, right? Half x squared. Agrees, everybody? And V0 is initially is this. So V dot, if I compute, what will be V dot? It will be dV by dx. That is x into x dot, right? What is my x dot? Minus x cube. It becomes minus x4. What can you say about V dot? It is always negative except at 0. Right? Always negative. What does this says about this energy? That means if V0 is a energy level here, right? It's a set where V0 equals to this half x squared. So you can draw this, right? Or at least in a scalar quantity, it means that V0 is here, right? So that means V dot is negative all the time, other than 0. That means V is always decreasing. So that means you start here, you're always jumping level curves, and it will go to 0, and when it is 0, then V dot is 0. That means it is not changing. So you reach. So that means you can prove somehow that if because of this nature of V dot to be negative, it will entirely lie in this subset. and then you can say that there is a unique solution for all time t greater than t0. That's a big statement. So you see how we started. Things are, of course we did all the definitions and all, but in real life nothing can be globally Lipschitz. So local Lipschitz is good, and for that all you have to check is it is continuously differentiable. That's all. This as soon as it is continuously differentiable, game over. It's locally Lipschitz. You should be happy, and then you show that the trajectory never leaves a complex set. If that additional condition can be imposed, then you have a unique solution for all time t greater than t0. Boom. Okay, so this is chapter 3. Gentlemen, homework is already posted for chapter 3. Well, it is interesting. Do you agree or not? Anybody is?
I mean, yeah.
It's might be a little bit work or something, but what are the assignments in 3 that I have given? I just want to make sure that I have a book here. I just want to see. Can you go to Canvas and see?
Yeah, I'm here now. So 3,
I just want to make
1,
sure that
3, 7, and 8.
I just want to make sure I don't give you anything. So you have 3-1.
3, 1.
You have 3-1, right? So in 3-1, you are just showing we have functions like 8 functions, and you are showing whether they are globally Lipschitz, continuous, and globally Lipschitz. Locally, continuous, globally Lipschitz. So you basically categorize each function based on whether it is A, local Lipschitz, continuously differentiable, definitely, B, locally Lipschitz, C, continuous, D, globally. So you use all these lemmas and theorems you have
Okay.
to just cite a particular theorem lemma whenever you're giving the solution, say. And what is the next one? So that's easy, 3.1.
Okay, 3, 3.
3.3, yeah, you can show that, 3.3, it will be a good problem. Next.
Okay.
That's-
7, and 8.
7 is continuously differentiable, unique solution, yes, that's good, 3.7, then,
And 3, 8.
yep, so yeah, all good, all are good problems.
You are so excited. Okay.
So yeah, I will post this. So now I want to compute, so what is my f of x? I will write again, or maybe we can just